I'm Michael Grossman. I'm with Aquafortus. And yeah, we're looking forward to working with the consortium later this year to do some sampling on our field research facility is kind of the name I call it, and we'll get more into why. But essentially, this deck gives you a quick intro into who Aquafortus is, who we are as a team, our history, our company, the desalination problem. Hopefully you guys are all familiar with that. I threw it in as a quick aside. We'll talk a little bit about it, but then the ABX process that we're using to address desalination, how and why it works, a little bit of some of our preliminary data we've developed so far from our piloting work, as well as the actual facility, the field research facility, and just a brief, like I said at the end, our piloting results. So, Aquafortus technology originally developed in New Zealand. My colleague, Dr. Richard Brunton, he's hiding in the back over there, one of the founders of the technology. Really cool technology for removing water. We'll get into how the process works. Originally developed for semiconductor and other facility industrial waste, but we've seen the applications in produced water and other markets in North America as being key to our business, and so we're building our US team. We're now a New Mexico-based company, headquarters in Hobbs, and unfortunately, we are currently doing the most of our work on the Texas side of the border because of some of those Water Quality Control Commission rules that Mike was not so subtly hinting about, but would love to be doing more work on the New Mexico side as a New Mexico company. Please stop me with questions and stuff. I feel like I'm rambling when nobody interrupts me, but if anyone has any questions, please let me know. So the desalination problem, quote unquote, right, especially for high TDS waters like produced water, right, the traditional ways of doing desalination, seawater RO, nowhere near applicable, or brackish water RO, they're not applicable in these waters, right? So you need specialty membranes, but the other challenges of membranes are, and so Pedro pointed out these things are membranes and thermal technologies are kind of the conventional ways this is treated. The problem with membranes in these extreme TDS waters, you need either ultra high pressure or osmotic assistance, something special on your membranes. You really need to protect them, though they're very susceptible to failure or just fouling, scaling, things like that. Thermal technologies, very effective at handling a wide variety of feed chemistries, but you need a lot of post-treatment and a lot of energy, right? So that's typically driving the cost of these projects is the energy involved in thermal desalination. So Aquafortus has tried to develop a solution that is not thermal or membrane, right? So, I hate to critique Pei, I'll just call her out again. I saw your slide had thermal or membrane. There's someone else out there, and there's some other technologies that are trying to get into the space too from outside that space, but Aquafortus has been running a solvent-based desalination process on Permian produced water, and I'd love to share more about that. So we call this solvent-based desalination or the ABX process, right? What is this? So essentially, it has three subcomponents, right? So the first step is dewatering of the wastewater, whether it's produced water or some other industrial water. And how do we do that? We put the wastewater in direct contact with our absorbent. So we have an organic absorbent that is drawing water out of the wastewater. So, and this is again, just a liquid contact process, step number one. You see pictures in a second, it's just vertical contact towers wherein the absorbent is fed from the bottom, our wastewater is fed in from the top. The produced water has a higher density, so it sinks to the bottom. The absorbent has a lower density, so it floats up to the top. And then we can skim off our absorbent and clean water from the top of the vertical contact tower. So that we take that and so that we can discharge things like salts, organics, all that stuff is not absorbed into the absorbent, and so they're rejected to the heavy brine at the bottom of that first tank. We can run this process. The key control step of our process is the ratio of absorbent to water. So hypothetically, if you put, 30, 40 parts of absorbent for every 1 part of water, what comes out is just salt, or you pull all the water out of your feed. And it just all it does is pull water out. It's just a liquid contact process by osmotic pressure difference. We draw water into our absorbent and out of the wastewater stream. And again, because it's an organic solvent, highly nonpolar, it's immiscible in the wastewater. So the heavy brine we're rejecting keeps sinking to the bottom, and we can just skim the absorbent plus clean water off the top. So that's step one. Step two, similar, it's a vertical liquid contact again, but now our absorbent and clean water are again put in direct contact with a regenerant, a second chemical. Now this is an aqueous solution, right? So again, very polar, very dense, and actually fairly viscous. So a little bit challenging mix. We actually have to really force these two fluids to mix because they really are miscible. They really don't want to mix. So we do have to add a little bit of mechanical mixing to force these two liquids to mix. But again, gravity separation, we can get the recovered absorbent, that organic solvent, right? We get that dewatered, and we can use that again in the process. So that kind of first loop, right? We're recovering the absorbent for reuse in our process. And then we have the regenerant. Now again, this is an aqueous phase regenerant. So we've diluted the regenerant with water. So it's essentially just a diluted version of the original regenerant. And we feed that diluted regenerant into step 3. Step 3 is just a membrane process. But again, this is just our diluted regenerant going into the membranes. This is not treating produced water. So there's no scaling salts, there's no organics, there's no chance of precipitated solids going into that third stage. So we just dewater the regenerant with a membrane process so we can recover clean regenerant for reuse in stage 2 and clean water at the back end of the process as our final product. Yeah. Yes. So and it's extremely modest, but yes. So, and that segues perfectly to what I wanted to say here. So thank you for that, for the perfect segue. So we do see a small amount of absorbent carry over from our process into the heavy brine. It's on the ppm level, but it is trace amounts, and but we do want to recover that, right? That's economically valuable to us. And so we have a polishing media that we treat the heavy brine, and this is not because we care about this is probably, in this application, this is probably just going to downhole. We don't really care about it, but for our economic value, we want to make sure we're covering it. So we have a regenerable media we use to recover absorbent out of the brine before it goes to discharge. We also, so after the wet absorbent, I don't know if it's fine. So after the wet absorbent goes over to the regeneration contactor, right? So that regenerant will also have a little bit of the absorbent left over, the wet regenerant. And so we also run that through a media so that, I went forward. So steps 2 and 4 are kind of just an additional, these are kind of the actual individual processes. That's just a kind of macro block flow picture. So is that kind of help clarify? We want to make sure for economic reasons we're recovering as much of these chemicals and keeping them within our system for techno-economic value. The regenerant is actually a food-grade additive, so theoretically, if we lost some to the discharge, it's not really hazardous to anything, but it's just for economic values, we want to make sure we're getting as much of it back into the process as possible. So again, this also creates a multi-step treatment process within our ABX process, right? These are all integral to making, these 3 steps are integral to making it all happen, but it also creates multiple barriers. So something like, a lighter organic phase, there are some light organics that will potentially dissolve into our absorbent, but they will not dissolve into our regenerant, right? And so they'd never reach our membrane at the end of the process because we have 3 steps of transfer of the water before it's clean water at the end of the process. So there's kind of multiple steps. And again, the polishing medias, right, can also potentially help recover these organic, any light organics that potentially are dissolved into our absorbent. Pose. Any other questions, Raj?
Hold on. Raj, before you...
Sorry, yeah.
Gotta go for the mic. There you go.
Did you mention solvent absorption or adsorption?
So I colloquially call this solvent-based desalination, right? Because we use an organic solvent for our absorbent, but it isn't, technically it's an absorption process.
And how is that, once it absorbs the water, how is that separation happens between the solvent and the purified water that is absorbed? How is that separation happens?
So in the absorption tower, the absorbent pulls water out of the produced water by osmotic pressure differential, right? But the 2 fluids are just mechanically mixed together. There's no membrane or barrier between them. So it's just mass transfer of the water that is in the water stream is pulled out by the absorbent. Again, the osmotic pressure of the absorbent is very high. It pulls water out of the produced water. If you just kept adding more and more absorbent, it'd keep pulling out water. The same process happens in number 3 here, the RDC, right? We're pulling water out of the absorbent with the regenerant by liquid-liquid contact. Again, it's an osmotic pressure differential, so we're drawing water out of the absorbent with an even higher osmotic pressure. With that concentrated regenerant has a very high osmotic pressure, and it's pulling water out.
Does pH play any role in it? Or do you have to be a certain pH in the initial stage or no?
PS, I'm sorry?
pH of the water?
No, I mean, we've tested a wide variety of pHs, I think 2 to 12, and really haven't seen, obviously material handling need to be concerned about, those types of pHs, but our absorbent is functional across all those pHs, and that's only affecting that first stage, right? The wastewater stream only comes into the absorption tower and the brine polishing, and then it's really our absorbent, our internal circulations are the rest of the steps, right? So that pH doesn't really affect the pH of the downstream processes, the regenerants and things like that.
Thank you.
Any other questions while I'm pausing here? Yeah, please.
Oh, sorry.
So,
Sorry, hold on, Pei. You have to use the microphone.
Sorry.
Yeah.
My question was really simple. What is the water recovery?
Yes, so we can vary the water recovery all the way up to and including zero liquid discharge. So the key is that ratio of the absorbent to feed water in that first step, so that as long as we keep adding more absorbent, it keeps pulling more water out, right? So we tweak that ratio based on how much water we want to recover. Our target in oil field is we want to minimize, we don't want to precipitate salts, but we want to maximize water recovery short of that. So hypothetically, right, so we've done a lot of work with this brine. It's about 120,000 milligrams per liter TDS. We can do up to 60% plus or minus water removal from that, but we obviously want to stop short of that salt precipitation, right? So plus or minus 280, 300 grams per liter, right? That we want that heavy brine to be short of salt precipitation for disposal purposes, not because it's a limitation of our technology. And again, I'll show this picture in a second, but we have developed this process, including on the site that I'm showing you guys pictures of, where we've run it to precipitating salts at the back end of the process. So we can get even higher than that 60% water removal if you want to manage salts. You just probably don't want to manage salts. So, sorry. Yeah.
Is there a temperature effect?
So we've run this. I don't know what we've done some testing actually at extreme low temperatures. We're looking at some projects in like tailings water up in Alberta down to like 2C, and so far we've performed successfully. I mean we've tested. I don't know what on the high end we've tested, but I know we tested up to 60C on the water temperature.
Thank you.
Yeah. A couple of online questions for you, Michael. Sure. There's 3 from Melissa. I think we're only going to just do 2 for time's sake, but the first one, just to be clear, you're using brine and produced water interchangeably.
Sorry.
So in other words, you're treating produced water, not brackish water, correct?
I apologize for that. Yeah, so I colloquially refer to all of our industrial wastes as brine, right? But I shouldn't. To be clear, in this application, we are talking about produced water. We've dealt with other wastewaters of that nature, but this application, we are talking about produced water. Yes, not brackish water.
Great. And then how are you defining clean water? What standards are you meeting?
So we'll present here some of the specific data here, but we have done TDS below 100 ppm in this testing here.
Actually, I also have the follow-up on the clean water. Even though your TDS could be low because you use organic solvent, so how about the TOC or other organic constituents in the water?
Yes, so that's a good question. So the organic solvent is miscible in the regenerant, and the regenerant is what's going to the membrane. So we really don't see absorbent going even in the feed to the membrane, let alone the permeate from the membrane. We do see, I think it's single-digit ppm of our regenerant in the treated discharge, like in the permeate from the process. But again, it's a very large. It's an organic molecule. There is our regenerant. What I'll say, it's an aqueous solution with this organic molecule. It's a very large and high charge density organic molecule in the water. So rejected by the membranes at extremely high rates, right? This isn't like a boron or something they're getting high membrane passage, and that's the regenerant. That's the vast majority of the constituent going into the membrane. It's not the salts from the produced water. It's not our absorbent. It's our regenerant. And it's designed to be rejected by the membrane and really be clean to the membrane, right? So we've demonstrated in the lab running membranes all the way up to, I think, 200 bar, so a couple thousand PSI membranes that with this specialty, our regenerant is very membrane friendly. So we can push the membranes very aggressively, continue to get rejection, and keep the membranes clean because the regenerant is designed for use in membranes specifically.
Has your effluent been tested? Has your effluent been tested through whole effluent toxicity?
No, it is not, and that is what we are hoping to work with the consortium on.
Oh, awesome. Okay, you're in the right place.
Hill, yeah. Oh, sorry, I'll let Zach run to you.
The organics in the produced water end up in the brine. Do I understand it correctly?
Yes.
Is that the RO membrane or like any microfiltration, ultrafiltration membrane?
So we've played around with different membrane configurations. We do need to remove dissolved species, so it is high pressure membranes, right? But we've played around with different salt passages, so a combination of nano and RO membranes. We've tested a variety of different configurations of nano and RO membranes, but it does need to be that type, not MFUF and nano or RO. Oh, we got a membrane question coming to me, I bet.
Yep, one more. You were talking about using high-pressure membranes. Well, that then increases your operational costs. Do you have an idea of what your operational cost of your entire system is? Not counting, trucking and everything else, just the equipment itself, so.
So I'm going to give you guys a ballpark number because I'm a nice guy, but there's going to be a million caveats to this, right? So when we talk about commercial scale operation, so plus or minus, say a 20,000 barrel a day feed unit, and again, plus or minus 50% water removal on like typical Permian produced water, million caveats on how you're depreciating capital, what your cost of energy is, like there's a million things. I don't want to, get myself in too much trouble here because there's a million caveats to this, but plus or minus, we've gotten our commercial scale design pricing, again, with installed capital cost and operating costs down to about $1.25 per barrel desalinated. Now we are actually pushing to get that lower because the industry has been telling, for 10 years now, if you can get to $1 per barrel desalinated, we'll build these things. I don't know if that's true, but we are going for that. We are pushing hard. We are making further optimizations too, and that's why I was a little yin-yang. I apologize for my vagueness on my answer to you because we were trying to optimize the design of our membrane system. That's one of our key features that we think we can bring price down on. We are trying aggressively to get below $1 per barrel desalinated. That is our goal in the next 6 to 12 months of R&D. We've demonstrated some things in the Auckland research facility, in the lab. We've not yet brought out to the field that we hope will get us there.
Michael, could you comment on one of the concerns we have with produced water and heating it up is materials we have to use in the thermal processes. Do you have any advantages there?
Absolutely. No, thank you for that. Yes. So, and Zach is hinting to me that I need to move on. I have like 7 or 8 more slides that I'm probably going to have to miss most of, so I'll apologize. If folks want to talk to me about the rest of this deck, it's public information I can share. I'm not clicking, my clicker's no longer working. I don't know what happened to me. But I just wanted to show a picture of the equipment before I kind of got cut off, like what this actually looks like. But basically, the first 2 steps happen in vertical contact towers. We are currently making those out of steel because of chlorides concerns. They're currently over-designed in the use of 316 stainless. We probably can get away with cheaper. So these are the vertical steel columns. There are 6 of them at this site. We've now optimized this same facility, could get down to 2 or less of those 6 columns, but that is what the current system is. And then membranes, right? So again, because we're at low temperature, but we are concentrating up to salt saturation, right? So there's a lot of chloride still, but in general, there's no heat added whatsoever in our process. So I'm not a metallurgist, but I previously did some thermal desal work, so I'm very familiar with the alloys involved in saturated chloride brines at plus or minus 80, 90 C, right? The metallurgies there are a fortune. So we need no special metallurgies here, right? We can build with stainless, probably can even build with cheaper than stainless if we needed to. But yeah, this is what the facility looks like. This is our 2,000 barrel per day, rated feed capacity unit. Right now, it is temporarily shut down, again, as we bring some optimizations to the membrane piece of the system, but it was running as of very recently. And again, this is kind of the general layout, right? So there are 6 vertical towers you saw there, and that is part of the ZLD design, right? So I call this the field research facility because we have tested a bunch of different configurations of this technology at this facility, including zero liquid discharge, including multiple different versions of that brine polishing step where we capture the extra bit of absorbent. We have multiple different technologies we tried out there. So there's some parts, and I lovingly call it vestigials. There's some vestigial features of this system that are no longer in use. And again, I can share this picture. This has kind of the details of which pieces we're actively using, which pieces were there and exist but are no longer in use. And Zach is going to kill me if I don't start talking faster, so I apologize. Again, our RO permeate from the discharge of the system, again, this is one of the key slides I want to make sure I hit, again, is less than 100 milligrams per liter TDS, but we have not gone through the full wet testing and other, biological testing, so would love to kind of get some outside validation. We are a relatively small startup company and just didn't have the assets in-house to do that full testing, so we appreciate the consortium helping us with all of that. This represents only 40% water removal. I will note that. The techno-economics do change quite a bit if you're getting 40 versus 50 versus 60% water removal on this same brine. Again, we can run this brine up to 60% water removal without precipitating salts, but the techno-economics on a $1 per barrel number were a lot more favorable at lower water recoveries. So if your goal is to maximize water recovery and you're willing to pay a little bit more, that's great, but we can do that type of evaluation too, right? Our system, again, it's just tweaking the internal recirculation flow rates, right? That absorbent to produce water flow rate. So if we tweak that internal recirculation rate, we can get different water recoveries. Energy consumption, again, this is a big piece of that cost. So right now we're at about 20, that system out there is running about 20 kilowatt hours per meter cube desalinated. So, what's it, seven barrels per meter cubed, right? So don't trust me on my back of the envelope math, but 2 point something, 3 kilowatt hours per barrel desalinated. Plus or minus, John's nodding his head. I trust John on unit conversions. So, but we believe, again, from theoretical calculations, we can get down as low as 10 kilowatt hours per meter cubed. So again, 1 point something kilowatt hours per barrel desalinated. The key there is that there's just a lot of inefficiencies of, if you see a picture of this unit, whoops, I'm going the wrong way. Anyway, if you see a picture of the unit, there's a lot of inefficiencies of the layout and design. There's some losses. We're actually underutilizing some of the equipment. The equipment was designed for even higher recirculation flow rates just in case we needed them that we're not using. So there's some inefficiencies that we've optimized for the next step that we think can get us closer. We're right in the lab, we're running at about 12 kilowatt hours per meter cube desalinated. And we think that that is a real number we're actually running. We theoretically think we get down to 10. So, yeah. That's kilowatt hours of electricity per meter cube desalinated. And yes, it's pumped energy, exactly. A little bit of energy. So I didn't get into this, but in order to get the regenerant and the absorbent to mix, we do require a little mechanical shearing, but I mean, that's like a fraction of, like single digits, like the percent of the energy, mostly pumping energy.
What are your mob times?
What are what, I'm sorry?
Mobilization times in and out?
So you mean the flow through the system? So
To move the location. Like
so this unit was built on site with a lot of inefficiencies and changes. I'm hesitant to ever move this from our research unit from our research facility. That's why I harp on it being a field research facility. We are building a dedicated single container mobile pilot unit that will be plug and play. So that is the goal. Is that a lot of folks have said, hey, can you bring this unit to our site? And I hesitate to offer that because of it's not optimized for movability right now, unfortunately.
So, sorry everyone, I think I'm gonna have to cut Michael off there. We are over time, so you can catch him at the break and corner him and ask him a bunch of questions, so.
I guess I'll leave that up there for a second.
Thank you.